Okay, let's go back to our merry-go-round example. So we got person on the inside, person on the outside, and the central area. We already talked about how even though their angular displacement is the same, so they'll cover the same angle, the one on the outside has to cover more distance. Well, keep in mind, after they've made a full rotation and end up back where they started, they would have the same period. So if we wanted to find like an average speed here, the average speed for each one would be the circumference that they make. And I spelled, yeah, whatever. Circumference divided by the time for one revolution, or rather the period. But we have to be careful here. I'm using a translational or linear distance. And what I mean by that is if I have the circle that they've made and I unroll that circle, so that begins to unroll, I'll get the distance of 2 pi r. So that's what I mean by linear. So this linear distance will not give us an angular speed, it will give us the linear or translational speed. Or one way to think of it is, if we're talking velocity, it would have a direction. Well, that direction is tangent to the circle, so we could say it's a tangential speed. So if the speed is uniform, then our average speed, again, if we have a constant velocity, what that means is the average speed will equal any of the instantaneous speeds. So this tangential velocity, if we have what we call uniform circular motion, the tangential speed will always be the circumference divided by the period, which, I mean, it's really just distance over time. And we know we can relate period to frequency. They're inverses, so it could also do 2 pi r times the frequency. But what I want to be careful about here is this just gives us the speed. If you'll notice, when the person on the outside gets to the other or to another part, I guess another location, like relative to our view, the direction has changed. So this is simply just going to get us the speed, it's not going to get us the direction. Since that's always changing, this tells us something else, that uniform circular motion is an accelerated motion. And according to second law, if we have an accelerated motion, we also have a net force. So we'll talk about that in a bit. But right now I want to get back to the speed itself. Keep in mind, 2 pi is the angular displacement. Actually, I want to go back. I want to work with the original equation we had. So we're going to work with the 2 pi r over t. So keep in mind, 2 pi is the angular displacement for that route. Well, if we look here, the angular displacement divided by the time, that is a velocity, or angular distance over time. That is a speed. So that is our angular speed times the radius. So that's one way we can go from tangential to angular. Just like we had our translational distance, we have our angular displacement or angular distance that we covered. I guess it's not really a distance, so we'll just call them displacements. In both cases, we can just multiply by r to get to our translational equivalent. I could talk about acceleration, but there's a lot of good derivations for the acceleration of an object moving in a circle. So I'm just going to leave that up to you. You're essentially looking for what's called the centripetal acceleration. And as far as the name, it just means center seeking or center moving, center heading. And if you brush up on your vector addition, I think the derivations will be pretty easy to understand. So I'll leave that to you. But if we have a centripetal acceleration, second law says we should have a centripetal force, and that'll be the topic of the next video.